You're going to be doing a lot with surface area in multivariable calculus. It's one of the really fun things. And just remember when it gets complicated that the simplest things are the most important. And the simple things are if you can handle things for linear functions, you know all the rest. So there's going to be some complicated stuff, but it'll really only involve what's happening on planes. So let's start with surface area. And the example that I'd like to give, this is the only type of example that we'll have, is a surface of rotation. And as long as we have our parabola there, we'll use that one. So we have y is equal to x squared rotated around the x-axis. Well, so let's take a look at what this looks like. It's the parabola, which is going like that, and then it's being spun around the x-axis. So it's some kind of shape like this with little circles. It's some kind of trumpet shape, right? And that's the shape that we're... Now again, it's the surface. It's just the metal of the trumpet, not the insides. Now, the principle for figuring out what the formula for area is not that different from what we did for surfaces of revolution, but it just requires a little bit of a thought and an imagination. We have a little chunk of arc length along here, and we're going to spin that around this axis. Now, if this were a horizontal piece of arc length, then it would spin around just like a shell. It would just be a surface, all right? But if it's tilted, then there's more surface area proportional to the amount that it's tilted. All right, so it's proportional to the length of the segment that you spin around. So the total is going to be ds, that's one of the factors here. Maybe I'll write that second. That's one of the dimensions. And then the other dimension is the circumference, which is 2 pi, in this case, y. All right, so that's the end of the calculation. This is the area element of surface area. Now, when you get to 1802, and maybe even before that, you'll also see some people referring to this area element when it's a curvy surface like this with a notation d uppercase s. That's a little confusing because we have a lowercase s here. We're not going to use it right now, but the lowercase s is usually arc length, the uppercase s is usually surface area. So, also used for dA, right, the area element. But this is a curved area element. So. All right, so let's figure out this example. So in the example is equal to x squared, then the situation is we have the surface area is equal to the integral from, I don't know, 0 to a, if those are the limits that we wanted to choose, of 2 pi x squared, right, because y is x squared, times the square root of 1 plus 4x squared dx. All right, remember we had this from our previous example. This was ds from previous. All right, and this, of course, is 2 pi y. Now again, the calculation of this integral is kind of long. And I'm going to omit it, but let me just point out that it follows from the same substitution, namely x equals 1/2 tan u.